Physical properties of these elements. First one is physical state. At room temperature, this fluorine and chlorine are gases. These are gaseous state. Your bromine is a, Br2 is a liquid in nature, liquid state. Now, I2, iodine is a solid in nature, solid nature. Now, this iodine I2 in a solid state, it shows one important, a very good important property, that is sublimation property. What is sublimation? Iodine shows sublimation property. Your sublimation property, sublimation energy, sublimation process. Whatever it at room temperature, this solid iodine is directly converted into iodine vapors. Without converting into a liquid state, direct conversion of solid to gas or the solid to the vapors without without converting into a liquid, that process is called the sublimation process, and the amount of energy required for the process is called a sublimation energy, SCE. For iodine at room temperature, some minimum amount of energy required at room temperature only. This iodine solid vaporizes, converted into a iodine vapors. Just like naphthalene balls. It is a solid at room temperature. Whenever that naphthalene ball or room fragrance, any balls, odonyl balls are exposed to the atmospheric air, they are easily vaporizes without converting into a liquid. That process is called a sublimation process. For that process, amount of energy required, that energy comes from where? From atmospheric air, from temperature, from atmospheric temperature, it absorbs, then converted into vapors. Now, between molecule and molecules, or between atom and atom, top to bottom already explained, like between X and X, like fluorine and fluorine, chlorine and chlorine, bromine and bromine, iodine and iodine. Bond length order bands increases. Between molecules and molecules, like X2 and X2. This is the halogen molecule and halogen molecule due to the presence of weak van der Waals forces between molecule and molecule. The weak van der Waals forces are there. Due to the presence of weak van der Waals forces in this halogen molecule, top to bottom size increase. Between molecule weak van der Waals forces decrease, they are easily vaporizes. Reason why it easily vaporizes, because they are iodine and iodine between weak van der Waals forces exist. That force is slow, that force is very less than compared to the fluorine, than compared to the bromine, than compared to chlorine. In iodine, that force is very less, that easily vaporizes. Between atoms and atoms, here fluorine and fluorine bond length is less. They are attractive in nature, more covalent in nature. Your chlorine size increases, covalent nature decreases. Now, between molecule means between fluorine, chlorine, bromine, iodine. Between molecule van der Waals forces decrease, because increasing this molecular mass. Then force decrease, that easily vaporizes. That is physical state. These are the gases, these two at room temperature. It is liquid and it is solid. Then generally here Second important point is non-metallic character. Non-metallic. So in this 17th group elements, all are almost all are non-metallic in nature, except astatin 80, because your 80 is a radioactive element. Radioactive element. Slightly its non-metallic character decreases. From your fluorine is more non-metallic than compared to the chlorine, than compared to the bromine, than compared to the iodine. All are non-metallic, but compared to that, while comparing, this is more non-metallic than compared to the iodine. Decreases, like. Clear? So your non-metallic and these are generally highly reactive nonmetals. Highly reactive nonmetals that are reactive nature also same order. More reactive than compared to chlorine, than compared to bromine, than compared to iodine. Now here due to the presence of one valency unpaired electron, and to get a readily octet electronic configuration, these molecules exist as a diatomic molecules. Diatomic molecules means your halogen molecules. Halogen atoms cannot exist. Halogen molecules. Your halogen molecules means X2 like. Between atom and atom, 7 valency electrons are there. Out of 7, one is unpaired. That one unpaired electron is ready to donate. It forms a covalent bond to attain the stable octet electronic configuration. Now, gives like X bond X. Now, this is molecular structure, Lewis dot structure. Here 2 electrons are there. Here it shares these X, shares these 2 electrons, and also these 2 electrons are shared by this X. So both are attains the stable octet electronic configuration. So ready to get a stable octet electronic configuration, your halogen molecules, halogens exist as a diatomic molecules and ready to attain stable octet electronic configuration. That's why they are highly reactive and non-metallic in nature. Clear? Then very important property is here about halogens. Color property. See it, color property. Color property of halogens. Your fluorine F2 is pale yellow or yellow in color. Now Cl2 is greenish yellow color it is. Now your Br2 is red color or reddish brown color. Now I2 is a violet in color, violet color. So the astatine is a radioactive element. Remaining all these are in gas or liquid or solid state exhibit some color property. This is. In practicals, in organic chemistry, chlorinated halogen atoms, any organic compound is present. Whenever exposed to the atmospheric, whenever exposed to the non-luminous flame of the Bunsen burner, like this is the non-luminous flame of the Bunsen burner, to this non-luminous flame of the Bunsen burner, to this by using a spatula, if we can just introduce chlorinated compounds. Chlorinated compound, organic compound, it imparts greenish yellow edged flame. For example, here C2H5 bond Cl, ethyl chloride. Take one liquid on spatula and expose to the flame, that is the non-luminous flame of the Bunsen burner. It imparts green edged flame. That green edged flame or a greenish yellow color flame indicates the given organic or any compound contain Cl. If it is bromine, yellow color. If it is if it is fluorine, yellow color. If it is bromine, reddish brown or the red color. If it is iodine, violet color imparts. That is one of the most indication preliminary tests to identify what type of halogens present in that organic or inorganic compounds. For example, here the NaCl is there, greenish, or NaF, sodium fluoride, yellow color. Sodium bromide is there, that is reddish brown color. Like here NaI is there, iodine, violet colors. That is reason for this due to the excitation of electrons from lower energy to a higher energy orbitals. So due to the excitation of electrons from lower energy level to the higher energy level orbitals, atomic orbitals, then it imparts certain colors. How it excites? Here fluorine or chlorine or bromine or iodine, whenever exposed to the atmospheric air, depending on type of photon. What is photon? Type of photon, that is called a quanta. Quanta energy is equals to h nu, photon, and h nu. Depending upon the type of photon absorbed from this sunlight or from a burner, depending upon the type of photon or the quanta is equals to h nu absorbed by these elements, it imparts different colors. So based on their frequency and wavelength of the visible light radiations, it absorbs that radiations absorbed by different elements, it shows different colors. So why fluorine shows yellow color, why not red color? Means its capacity of fluorine absorbs the photons at a wavelength or the frequency radiations, it imparts certain different colors, like fluorine is yellow color, chlorine is this, bromine is this, iodine is this. That's why different photons absorbed by different elements, it shows different colors, not the same colors. Very, very important concept, color property of 17th group elements. The next one is some important simple points about 17th group elements, that is density, melting points, boiling points, bond dissociation energy, and solubility. Very, very important. So here next property is here density of 17th group elements. Density is gram per centimeter cube units. Now density is equals to, we know, mass by volume. Mass by volume. Now here the fluorine, chlorine, bromine, iodine, and astatine like. Now here the top to bottom are fluorine to the iodine, atomic number what happens? Increase. Simultaneously atomic number increase, simultaneously atomic mass increase, simultaneously atomic volume proportionately increases. So due to the increase in atomic number as well as atomic mass, proportionately volume increase, total density increases. That's why fluorine is less than chlorine, less than bromine, less than iodine. That is density. Then here melting and boiling points, both are the same order without any change. Melting and boiling order in kelvins are the same. Fluorine is less than, chlorine is less than, bromine is less than iodine. because top to bottom atomic number and mass increase, their boiling and melting points increases. Next one is solubility. Very, very important this is. Solubility of halogens. Now, your X2 is a generally X bond X. It is a non-polar. Non-polar in nature it is. There is no charges because both are having same electronegativity values. Generally, your F bond AF, like F2 molecule, it is F bond and AF. Both are having same electronegativity. Same electronegativity values means there is no charges, there is no poles. That's why they are non-polar in nature. Generally, solubility depends on like dissolves like property. Like dissolves like property, this is. Like means you are the polar compounds soluble in polar solvents. That is like. See here, polar compound soluble in polar solvent. Polar. That's why like. Now, your NaCl is a polar, that is soluble in H2O, is a polar solvent. Okay. Similarly, non-polar compounds or molecules are soluble in non-polar solvents. So here halogens like X2, chlorine, bromine and iodine are non-polar compounds or the molecules which are soluble in non-polar solvents. Significantly, it is non-polar solvent, that is in chloroform, like CHCl3 chloroform, carbon tetrachloride, benzene, like carbon disulfide, acetol, like in this molecule, the readily soluble. But less significantly, it is soluble in water. So are they negligibly soluble in water at room temperature, because not significantly, less significantly it is soluble in water. Halogens, when dissolved in water H2O, they are less soluble, not more soluble, not significantly soluble in water, because it is a non-polar in nature. It is a polar in nature, like. It is a polar solvent. So based on this, we can explain easily oxidizing property. Next, in coming important property, I'll explain oxidizing property of halogens. On the basis of solubility also, we can explain. I'll repeat once again this. Now, based on this solubility, whenever these X halogens are soluble in non-polar solvents, such as non-polar solvents means here chloroform, carbon tetrachloride. This is carbon tetrachloride, chloroform, carbon disulfide, or benzene, like it is readily soluble, more soluble in nature, and these solutions impart some colors, that is due to charge transfer phenomenon. Charge transfer phenomenon, not excitation of electrons. Very, very important. Some solutions, whenever halogens dissolved in such a non-polar solvents, it imparts some colors, that is due to the charge transfer phenomenon, not a DD transition, not excitation of electrons. How it transfer means this molecule halogens receives the electrons from solvent, it forms a coordinate bond like. Now charge transfer from solvent to this molecule, then it imparts certain colors. That is due to the charge transfer phenomenon. Very, very important. Your solubility, based on solubility, your halogens are less soluble in water because it is polar, it is non-polar in nature, but readily soluble in non-polar solvents. Clear? Then next important thing is very, very important. We can expect one question based on bond dissociation enthalpy. See here, bond dissociation enthalpy, bond dissociation energy or enthalpy, that is we can express in kilojoules. Now your X2 is nothing but your fluorine, chlorine, bromine, iodine like this. Now here the fluorine bond of fluorine atomic size is like. Now here the chlorine and chlorine like. Your bromine and bromine like size increases. Iodine and iodine again size increases. What happens? Top to bottom atomic number increase, simultaneously atomic size increases, because a newly added electron enters into a new main energy level. So between iodine and iodine, yeah, the size increases like top to bottom. This is maybe nucleus, this is the iodine like. Yeah, nucleus. Year to year distance increases. Whenever top to bottom distance increases, this is ready to decompose, dissociate. Less amount of energy required. So by using a simple analysis between fluorine, fluorine, chlorine, chlorine, bromine, bromine, iodine, iodine, based on their bond sizes, which one has a higher energy, which one required higher energy to break a bond between fluorine, fluorine, or halogen atom and halogen atom? Between fluorine and fluorine, more amount of energy required, because they are a shorter distance, strongly attracted with each other. To break that bond, more amount of energy required. But whereas in case of iodine, less amount of energy required. Bond dissociation energy is nothing but the minimum amount of energy required to break a covalent bond between two atom of an elements. Exists between two atom of elements, some amount of energy required. So are the top to bottom size increase, bond dissociation energy what happens? Decrease. Originally by using this, your fluorine is less than, chlorine is less than, bromine is less than iodine, this is. Sorry. Originally for fluorine is greater than, chlorine is greater than, bromine is greater than iodine. Originally it is correct based on their sizes, but experimentally this is absolutely wrong analysis. This is the wrong order of bond dissociation energies. Reason behind that, very, very important 2 marks question. The correct order is for Cl2 is greater than Br2, then F2, then I2. This is the correct order. Bond dissociation energy order. Generally, they'll ask why the bond dissociation energy of fluorine is less than chlorine. Give reason. Actually, ಜಾಸ್ತಿ ಇರಬೇಕು. So actually it require more amount of energy, because between fluorine bond distance is less, then attractive forces are more amount of energy required, but experimentally that fluorine molecule require less amount of energy than chlorine. The reason behind that, here in case of I'll explain here, in case of fluorine, even though small in size, there is a less attraction, because your fluorine containing 7 valency electrons, and remaining fluorine contains 7 valency electrons. Between fluorine and fluorine, there exists even a covalent bond. By mutual contribution, mutual sharing, it forms one covalent bond. Here remaining 6 electrons are there. Here 2 electrons, here 2 electrons, here 2 electrons. Now these 2 electrons are equally shared by these 2 atoms, like, and also like this. So due to the small size of F fluorine, yeah, the occupied space is less between these electrons, and between these 2 electrons repulsions takes place. That is due to the interelectronic repulsive forces. Interelectronic repulsive forces, they are not strongly attracted, they are weakly attracted. That's why less amount of energy required to break a bond between fluorine and fluorine. So actually between fluorine and fluorine, small in size, they are strongly, tightly attracted, strongly bonded. But whereas in this case, particularly fluorine and fluorine, due to the presence of more number of valency electrons, and small in size of fluorine, between fluorine atom and fluorine atom, between electrons and electrons, repulsions takes place, not attraction, repulsions. That is called a interelectronic repulsive forces. So due to the more interelectronic repulsive forces, bond dissociation energy of F2 is less than Cl2 and Br2. This is very, very important reason. Give reason, or why fluorine has less bond dissociation energy than compared to chlorine. Give reason. A reason is due to the interelectronic repulsive forces, more interelectronic repulsive forces between fluorine atoms than in chlorine. That's why fluorine generally has less bond dissociation energy than compared to the chlorine and bromine. This is a very, very important question based on bond dissociation energies. Clear? Next one is clear? Now another important point is variable oxidation states by halogen's 17th group elements. Variable oxidation states of 17th group elements. Now here the 17th group elements are like fluorine, chlorine, bromine, iodine and astatine. Okay. So here first element is fluorine. It always exhibit -1 oxidation state, always. In all other compounds, there is no variable oxidation states for fluorine. So the fluorine always exhibit -1 oxidation state, always in all compounds. Fluoride compounds always exhibits -1. That is due to its small atom, small size, and high ionization, high electronegativity and high ionization energy. Compared to all known elements, highest electronegativity element is fluorine. Its value is 4. So due to its small size, high electronegativity and high ionization energy, it always in its compounds exhibit -1 only, do not exhibit do not exhibit variable oxidation states by fluorine atom. Then here chlorine, bromine and iodine, based on their combining capacity with the other atom of elements, it shows -1, +1, +3, +5, +7. These are the possible variable oxidation states exhibited by chlorine, bromine and iodine. Particularly your chlorine, bromine also exhibit your +4 and +6 also in oxides or oxo acids. I'll explain these oxides and oxo acids. Now these are exhibit in interhalogen compounds. What are interhalogen compounds? I'll explain. Interhalogens, oxides and oxo acids. Now here fluorine only -1, but chlorine, bromine, iodine shows -1, +1, +3, +5, +7. Chlorine also shows +4 and +6. How it exhibit -1, +1, +3, +4 and +7 oxidation states? I will explain that by using their electronic configurations, how it excites, how it shows +1, +3, +5, +7 oxidation states by chlorine, bromine, iodine with the help of electronic configuration. I will explain it. Okay, listen carefully. Note on these three important points, very important points. These, based on their electronic configurations, here electronic configuration of 17th group elements, general electronic configuration is NS2, NP5 is the electronic configuration. There exists a ND also, except fluorine. Now for example here, if it is fluorine, its electronic configuration is like, its electronic configuration is like, this is for fluorine, like. Your absence of d orbitals, absence of d orbital in its valence shell, your only this one electron is unpaired. This one electron ready to accept the electron from other atom of elements. After gaining fluorine atom, it becomes F-1, fluoride ion, that is equal to neon electronic configuration 10. F is 9 electrons are there. Now atomic number is 9 only here, but a number of electrons are 10 electrons are present. F-1 and neon are isoelectronic species containing both are having same number of electrons in its atomic in its valence shell. So based on this, your F fluorine do not excite any electrons from lower energy level to the higher energy level, like there is no excitation, absence of d orbitals, do not show variable oxidation state, only one electron says. That's why it shows always -1 oxidation state, always exhibit -1. Whereas in case of chlorine, bromine and iodine, general electronic configuration, I'll write here NS2, here NP5 and ND is there here. Presence of vacant term, d orbital in outermost orbits. Now this is the general in ground state electronic configuration. It contains 7 valence electrons, like depending upon the combining capacity. Now it ready to accept 1 electron. It shows -1. Or if it is ready to donate 1 electron, it shows +1 oxidation state in ground state. Okay? If it is in first excited state is nothing but your one electron excited from NP to ND. Now here NS2, NP4 and here ND1 electronic configuration. Here are 2 electrons. Here 4 electrons are there, like these are the 4 electrons, and here 1 electron is unpaired, like these 3 are unpaired electrons which are ready to donate. So in ground state, ready to receive 1 electron, -1 exhibits, or if it is ready to donate electrons to the other group, these 3 unpaired electrons ready to lose, it forms +3 oxidation state, first excited state. Now in second excited state, its electronic configuration is NS2, NP3, ND2 is the second excited state electronic configuration. Here 3 unpaired and here 2 unpaired electrons are there, like 1, 2. Here total 5 unpaired electrons are there. So in ground state, it ready to receive -1 or ready to donate +1, like here also +1, but after donating these 5 valence electrons, it shows +5 oxidation state, +3, +1, +1, +3, +5 oxidation states. So 1, 2, 3, 4, 5. Then third excited state. In this third excited state, its electronic configuration is NS1, NP3, your ND3, your 1 electron unpaired, your 3 electrons are unpaired. Now here also 3 unpaired electrons are present. So finally 1, 2, 3, 4, 5, 6, 7. Now shows -1. According to this +1 also +7 oxidation state. Now in chlorine, bromine and iodine, in addition to the -1 oxidation states, it also exhibits +1, like +3, +5, +7 oxidation states. So based on this, we can easy to estimate its hybridization also. Already in 15th group elements, like PCl5 explain, like how it excites. Same similarly, your IF7 is there, like in this IF7 one molecule. In this IF7 molecule, that is interhalosine compound, this fluorine is always -1 because highest electronegativity element small in size. Compulsory iodine shows minus, so plus. So by crisscross method, by using this I plus 7, F minus 1, then we'll get I1 F7, means iodine in third excited state. This is in third excited state. 1, 2, 3, 4, 5, 6, 7. With these 7, here fluorine, 7 fluorine atoms are covalently bonded. It forms like sp3d3 hybridization here. Here it is sp3d2. Here it is sp3d. Now it is sp3. So hybridization also we can easy to estimate sp3d3 because 3 orbitals are participated. In this IF7 also same thing, around I7 unpaired electrons are there, like these are the 7 unpaired electrons. 7. All these 7 are like this, 1, 2, 3, 4, 5, 6, 7. that is in third excited state. But here the fluorine contain 7 valence electrons out of 7. 3 are the pair, 1 is unpaired. Like now this is bonded with iodine. Similarly, this is fluorine. This is fluorine. This is fluorine. Fluorine. Here fluorine and it is fluorine. Now around iodine, how many electrons are there? Means here 14 electrons are there. Because 7 from iodine, 1, 2, 3, 4, 5, 6, 7. Remaining 7 are from fluorine, like to get the covalent bond. Total 14 electrons are present. Do not show any octet electronic configuration. It contains 8 electrons, then only obey the octet electronic configuration. That is a limitation. More than 8 electrons, 14 electrons are there. Do not obey octet, limitations of octet electronic configuration. But whereas in this case of fluorine contain 8 electrons. Like these are the 6 plus these 2 electrons, 8 electrons are there. But according to octet electronic configuration, in a molecule, central element containing 8 electrons, then only obeys the octet electronic configuration. That's why these IF7 do not obey any octet electronic configuration. Clear? Now, this is the variable oxidation state and excitation of electrons. While writing some molecules, interhallogen compounds, we want like excitation. Fluorine do not show like excitation because of absence of d orbitals. A very, very important concept. Wherever or whenever required, there I will explain complete analysis about this excitation of electrons. Okay. Next, last important, one important property is oxidizing nature of halogens. Oxidizing property of halogens. Are oxidizing nature of halogens. So this oxidizing nature of halogens we can explain on the basis of electronegativity, size, here hydration energy, here SRP values. SRP is nothing but S stands for standard reduction potential values. So here what is SRP or RP reduction potential and also SOP oxidized potential. Under standard conditions, how to calculate? S stands for standard, R reduction, O stands for oxidized. Same similarly, here reduction and oxidized both are having same values, just the sign only differs. How to calculate these SRP values or SOP values? We'll explain in electrochemistry in second year only. In electrochemistry, physical concept I'll explain. Don't bother about these SRP values. Just I'll give just a simple clue about this. So here oxidizing nature of halogens means your halogens are fluorine, chlorine, bromine and iodine. Astatine with radioactive elements. Your strongest oxidizing agent is fluorine than compared to chlorine than compared to iodine. So to explain this oxidizing nature of these, some reasons are there. High electronegativity elements, small in size, high hydration energy, and high hydration energy of this, and higher SRP value of fluorine. This value is SRP value is denoted by E naught, that is 2.87 volts. V stands for volts. Now this value is E naught value is 0.54 volts. Only for understanding purpose only, higher value, lower value. Higher the SRP value, higher its oxidizing power. That's why it is the strongest oxidizing agent. So here in a solution like F2 acts as a strongest oxidizing agent. Strongest OA oxidizing agent it is. So on the basis of all these, like an important example is here. Here lower atomic number halogen oxidizes higher atomic number halide ion. Very, very important this is. Halide ion. This is. So the lower atomic number halogen oxidizes higher atomic number halide ion. For example, here the halogens are fluorine, chlorine, bromine, iodine, like these are the halogen molecules. So compared to the chlorine and bromine, iodine, lower atomic number is fluorine. Clear? Now that fluorine have to react with NaCl, sodium chloride. Here are the 2 moles of sodium chloride. Sodium is +1. Chloride, it is not a chlorine. Do you know the difference between rin and ride? Now here Cl2 is a name is chlorine molecule. This is chlorine. Here the Cl minus is chloride. Chloride ion it is. IDE, chloride and chlorine. Rin is a molecular state. It is molecule. Chlorine molecule. It is a chloride ion. Ionic state it is. Now here lower member atomic number halogen. Halogen means like this is the fluorine, lower member. This is the higher member. Oxidizes higher atomic number halide ion. Halide ion means this is the halide ion. Oxidizes. See here, your F is a 0 oxidation state, but in case of chloride, Cl is -1. Then it gives 2 NaF. Sodium fluoride plus Cl2 is formed. Here it is 0. See here, fluorine molecules to 0 to here -1 is there. It is. What happens? Addition of electrons takes place. Addition of electron is nothing but reduction. In reduction process, the participated molecule acts as a oxidizing agent. That's why fluorine is less atomic number halogen atom, easily oxidize higher atomic number halide ions. So are the fluorine molecules to the fluoride ion, what happens here? reduction reaction takes place. In reduction process, participated molecule or species acts as a oxidizing agent. Now here Cl minus 1 to the Cl0. Removal of electron, oxidation reaction takes place. Now in this oxidation process, the participated Cl minus ion acts as a reducing agent, Ra. So here the molecule acts as the strongest oxidizing agent. Same, for example, Fa acts as a oxidizing agent, whereas F minus 1 acts as a reducing agent. Same, similarly, if you can take continuously like F2 is react with 2NaBr, sodium bromide. It gives 2NaF, sodium fluoride plus Br2. Here the Br2 gas is liberated. Here F2 reacts with 2NaI. Gives 2NaF, sodium fluoride plus I2 gas is liberated. For this connectivity link, I'll take one more. Here the Cl2 plus NaF. Is it possible reaction? Statements here. Lower atomic number halogen oxidizes higher atomic number halide ion. It is a atomic number is 17. Its atomic number is 9. Lower atomic number oxidizes to a higher atomic number halide ion. That's why this is not possible. When it is possible means Cl2 combines with the NaBr. It gives. Because it is 17, lower atomic number oxidize, higher atomic number 35 days, bromine. See here, fluorine with the chlorine, bromine, iodine. Chlorine is with the bromine and iodine, NaI, 2NaI. It gives 2NaCl plus your Br2 is formed. Your 2NaCl plus I2 is formed. So by using this same combination, here, I'll take one more important example is your Br2 reacted with 2NaCl is not possible. Why? This is the higher number, atomic number. It is lower. Compulsory here, what happens? Lower atomic number oxidizes higher. That's why it is not possible. Here Br2 react with 2NaI. Now it is possible. Because it is 35 only. To the 35 add here again 18. 53 atomic number. 53. So the lower atomic number halogens oxidizes, higher atomic number halide ion, it gives 2NaBr plus your I2 is liberated. This is complete oxidizing nature of halogens. So on the basis of chemical reactivities, on the basis of electronegativity, small in size and hydration enthalpies, we can say F2 is the strongest. Same on the basis of SRP values, F2 is the strongest oxidizing agent. Okay, these are some important points about 17th group elements, some physical and chemical properties. Last only one simple point, that is anomalous properties of fluorine. Anybody here just identify anomalous properties of nitrogen, already explained to you. Anomalous properties of oxygen also explained. Then right now in 17th group elements, anomalous properties of fluorine. See anomalous properties of F2 fluorine. Means this fluorine shows some peculiar properties then comparing with the other members of the same family, chlorine, bromine, iodine like. Why it shows anomalous properties means due to its first thing is small size. First one is small size. Next one is high electron negativity and ionization energy. Then third one is unavailability of d orbitals in its valency shell. That is the main reason. And also here the low bond dissociation energy. Low bond dissociation energy of fluorine. Bond dissociation energy of fluorine shows some peculiar properties. Fluorine with other important elements. For example, one simple example I will give here. So generally, the fluorine generally high electronegativity is there. Means it is generally more reactive. Generally has high electron negativity and ionization energy, and it is more reactive means acts as a strongest oxidizing agent than generally having Cl2, Br2 and I2. This is. So comparing the Cl2, Br2, I2, more reactive, high electronegativity and high ionization energy, strong oxidizing agent. But compared to the other elements, fluorine having low bond dissociation energy, B. So the energy is very, very less, and it forms only one oxo acid, whereas other elements Cl2, Br2 and I2 forms number of oxo acids. So there are some important differences with the other members. Now here the HF is a gas. HF is a liquid in nature at room temperature, whereas HCl, HBr and HI are generally gaseous in nature at gaseous state at room temperature. Why are the fluorine combines with hydrogen, it forms HF like HCl, HBr, HI. Why the difference between these two means here in this case hydrogen fluoride and hydrogen fluoride, there exists a intermolecular hydrogen bonds. So due to the presence of this intermolecular Hb hydrogen bond, it is exists a liquid state, remaining these are gaseous state. There are some differences between fluorine and other important elements of 17th group elements.